Thank you, Dean. And you did get the last name almost right, so that was great. And okay, so can everybody hear me? Okay, cool. So good morning, everyone. And first of all, thank you to the organizers for picking this paper and for inviting me to this conference. It's my first time here, and I'm very excited to be here and look forward to all the interactions today. And thank you for all of you for coming here early in the morning, especially to all the West Coast people. Coming from West Coast, I can see it's like really early. And today, as you can see, I'm going to be talking about a problem which is, I would say, something common and very often faced by experimenters, which is interference bias in experiments. And today I'm going to be talking about, this problem itself a little bit in the context of ranking algorithms, and also talk about one potential solution which can help mitigate this bias in certain situations, and how do we go about doing this. And this is joint work with my colleague Ali Goli, who's also at UW, and Anya Lambrecht at London Business School. Okay, so to jump in, we, ranking algorithms are everywhere. Pretty much all digital platforms use them. They're at the core of all the digital marketplaces. And essentially, the way they work is that users go to a website, they're either directly shown some kind of rank-ordered list of items, or they go there and query something and then are shown a rank-ordered list of items. And these rank-ordered lists are powered by different ranking algorithms. And because that's the main way in which users often start interactions with these platforms, the understanding or the expectation is that they often can have a big impact on both user engagement on the website as well as on the platform revenues themselves. So the platform's goal, most of these platforms, then the goal then becomes, how do you pick the best ranking algorithms among a set of algorithms you might have, based on however you designed them. And the goal in this process really is that what the platform is often trying to do is to figure out what would be the performance of an algorithm if it was deployed on the platform at scale. So if all the users who came to the platform were shown results based on this given algorithm, how would, what would some metrics that you care about, how would they look like? And this overall, outcomes that you care about, whatever they might be, clicks, revenue, whatever is of interest to you. I'm going to call it the total average treatment effect with some abuse of notation. You can think of it as the total reward or the expected value from deploying this algorithm. So then the question becomes, if you have a set of competing algorithms, how do you actually go about picking this? And the standard practice, as we all know, is to run an A/B test, which is you might have 2 or 3 or 4, any number of algorithms. You assign some subset of the traffic to one algorithm, another subset to another, and then you see, monitor some outcomes, and then pick a winner based on that. Based on whoever is doing well on this outcome. And the caveat, of course, here is for this to work, and the assumption that we are making is that the performance that we are seeing in the A/B test of this algorithm is the performance you would see if it was deployed on the entire platform. And one fundamental assumption which is going in here is, as we all know, the Sutwa assumption, which is that even though there are multiple algorithms being tried in parallel, outcomes under one algorithm are actually not affecting outcomes under another algorithm, because that's what would happen if you did deploy it at scale. So this is a critical assumption. And the question is this assumption valid in marketplace settings, and to what extent? So what I'm going to do is show you a very, very simple example in a very simple setting to show you that, even with very basic assumptions, how this assumption, how the Sutwa assumption can fail. So what I have here is a baby platform with 3 hotels. So think of it as like a travel website. And this platform has 3 hotels that it can list, A, B, and C. And that each hotel has 1 room that it can sell. So there is a supply constraint here. And the platform has 2 users. And it wants to test two different algorithms. So one algorithm is going to rank them as A, B, and C, and the second algorithm is going to rank it as C, B, and A, just the flip, okay? And again, in this very simple setting, users have no hotel-specific preferences. If they come in, if they come in and they see something at position 1, they click on it and purchase with probability 1/2, then position 2 with 1/4, and position 3 at 1/8. Okay, so it's a very simple setting. And the goal that the platform has is to figure out what would be the total average treatment effect of going with one or the other algorithm. Okay, and so what it wants to know is if this algorithm, so let's say we are focusing on algorithm 1, if its algorithm 1 is fully deployed at scale, then what would be the total average treatment effect of this? So here, as you can see, I clearly don't know how to use clickers. So here, as you can see, what's happening is that the first user comes, and if you're just looking at the first hotel, let's say Hotel A, they buy the room at the top with probability 1/2. When the next user comes, this hotel is likely sold out with probability 1/2, which means that the next user can only buy it with, it's available with probability 1/2, and then they purchase it with probability 1/2. So you can see that because there was this supply constraint on the hotel, the second user may not actually always have the hotel room available. And that is something which is likely to happen when you have fully scaled it up. So the demand per user is, taking that into account. In contrast, if you actually were to do an A/B, what you would observe in an A/B test is a scenario like this, where with 1/2 probability, user 1 gets the first algorithm and user 2 gets the second algorithm. So user 1 gets the algorithm 1, and we are looking at demand for product A, which is Hotel A. Again, they click on it with probability 1/2. But there is also the flip, which can happen, that they are assigned the other way around. And here, what you see is that the other algorithm is demoting this Hotel A, right? Which means that, therefore, the supply constraint in this A/B test is going to seem more slack, or in some ways laxer, than it is in the actual deployment of the algorithm. So you'll see that the expected demand that you calculate for this hotel is actually different here than what would happen if you had deployed it at scale. And that's basically the intuition. So this was a simple supply constraint issue. Because one algorithm is demoting this, and the supply is constant within a hotel, and these items, there is interference happening from this, and that's what's happening here. Now, that's for the first hotel. You can do this for the other two hotels we had in the example as well, B and C. And what you see is that Hotel A's supply is, in some ways, state is overestimated, whereas Hotel C, which was at the bottom, is going to get underestimated, whereas the hotel in the middle, which was Hotel B, is the one which is actually not getting an unbiased estimate. And this is interesting, and you'll see that this kind of forms the intuition behind some of the solution that I'll present. And the idea here is that the Hotel B's position in algorithm 1, which is the algorithm we are interested in, and in the overall A/B test, is unchanged from what it would be if this algorithm was fully deployed. So, so in this case, we are able to estimate this effect in an unbiased way. So this was one example of a source of interference bias, which is some supply constraints. But if you think of marketplaces in general, there are many other sources which can come into play. For example, other types of supply-side responses. You might think of promoting a small, high-quality, low-price seller to the top, and there might be high demand response, a lot of people buy, but the next thing you know, they might raise prices. or the reviews might change, and those are going to be endogenous responses which happen at scale, which you might, again, your A/B test is not capturing that. There could be feedback loops between algorithms. So at a fundamental level, these kind of A/B tests are unable to capture what the counterfactual market equilibrium would be when any ranking algorithm is scaled up. And so we are obviously not the first to think of this problem. This has been discussed in a variety of settings, and people have shown that interference exists, and both using data as well as simulations. And much of the literature has looked at how you can modify experiment design to address some of these issues. And what we will do here is, because it is a ranking algorithm and not item level randomization, these kind of solutions tend not to work so much here, and especially in a marketplace setting. So our solution is going to be slightly different. It's going to be more about, taking existing, you might say, flawed A/B tests and trying to see if you can do some bias correction to fix some of these issues. So it might, not take you all the way, but it will take you a good distance. That's the idea. Okay, so what we are going to do is, quick summary, show that this, formally established, like what I was showing you using the simple example, you can show that much more formally in like a much broader set of scenarios, and then provide a solution which exploits some of the intuition from the market equilibrium concepts that I was talking about earlier, and apply this to a travel website and show you, to what extent how much bias seems to be there and to what extent can be corrected. Okay, so the solution concept that we are going to use is going to kind of build on one key idea, which is that if the same algorithm was tested in multiple experiments, and if you can pool observations across these experiments such that some portions of these observations in these experiments are closer to the market equilibrium that would happen when you fully scaled up versus not, then you are, you can get a, corrected version of the estimate. So here is a, the same, using the same example, here is kind of the intuition. So if you had, so if what we had in mind was algorithm 1, which is what we were interested in, now if the same algorithm was now tested, you ran it, you use it in multiple experiments, experiment 1, like 1, 2, and 3, which I'm calling cohorts here. So you can see that in cohort 1, hotel B is position in the algorithm and in the overall experiment is the same. Whereas similarly for hotel A in cohort 2 and hotel C in cohort 3. So now think of these as like, if you can think of each of these like highlighted parts as like a micro like slice of an equilibrium. And if you're willing to make the assumption, and it's a big assumption, but if you're willing to make the assumption that item level demands are independent, so there is no like spillover, like no local interference effects, then you can think of intuitively like take each of these like highlighted blue areas and you can smush them together, and that should give you a estimate of the Tate when this algorithm 1 is scaled up. Okay, so that's kind of the intuition. So there are some useful properties of this algorithm, of this approach. The first is that you can become agnostic to the source of interference bias. So it could be through prices, which is like an endogenous response. It could be through supply constraints. It could be through feedback loops. And it doesn't matter so much. You don't need to know the algorithms themselves. Only the distribution of the ranking outcomes matter. Right? And finally, you don't need to kind of try to think about a new way to run experiments. If you have existing experiments and if you've already run, if you're willing to run, as long as you're willing to run repeat experiments with the same algorithm, you might be able to use the solution. Okay, so so now let me show you how the application to one specific setting worked with this algorithm. So this was an online travel agency. Think of it as something like Expedia or TripAdvisor. It's neither of them, but think of it as something where you go, it's a travel, you see hotels, and then you can search for hotels in a certain location, and you see these rank ordered lists. Okay, and this platform was interested in the performance of like many algorithms, but one focal algorithm of interest. We are calling it Genesis, and they ran many experiments using this algorithm. And they were tested against a variety of like algorithms that they were just designing, trying to see if they would do better. And they never really scaled this Genesis algorithm all the way to the entire platform. So we are basically in the data going to see a series of contaminated measures of the state of this algorithm. So this picture shows you on the top panel, it's showing you the portion of the traffic which was allocated to this algorithm across all the experiments. So they ran about 16 experiments, and you can see that there is a lot of variation in how much traffic they allocated to this algorithm. And what's interesting is that you can also see, which is how in some ways this research started, is that the performance of the algorithm itself seems to vary a lot from one experiment to other, which shouldn't happen if there was no interference, right? And what is particularly salient is this last two cohorts, last two experiments. So you can see that they were allocating about 60% of the traffic to this algorithm, and it was doing reasonably well. So here, 60% traffic is doing reasonably well. They're like, this looks great, let's scale it up to 80% of the traffic. And here they've scaled it up now to 80% of the traffic, and boom, the next thing, like there is a discontinuous and big drop. Okay, so this is this was kind of where this started as to why is this happening. So the question you might ask is, okay, there are many reasons why this could happen. In the paper, we talk about this in much more detail, but a fundamental question is this interference? Is interference causing this? And there are many ways to test this, and without getting into too much details, but one very intuitive test you can ask is, according to what we saw earlier, or at least the solution concept that we are thinking of, if it is driven by interference of like this difference in rankings and between algorithms, then we should see that hotels or items which have high ranking discrepancy between the focal algorithm and the rest of the cohort, right? Those we should see much bigger difference in performance than hotels like this Hotel B, which have low ranking discrepancy. Their performance should not have changed as much, okay? And that's something we test. We basically define measures of metrics for rank discrepancy, and then we do a median split. And what we find is that hotels or items which had high overall discrepancy, you can see these like red dots, their performance seems to discontinuously change from one cohort to the other one doesn't seem to change as much. So at least this is, I would say, some evidence that there seems to be some systematic way in which this behavior is changing. So there is evidence that interference exists, and we do have this data set where the same algorithm has been tested repeatedly against multiple other algorithms. So the question is, based on this solution concept that we had, what can we do to come up with a bias-corrected version or estimate of the state? And what we essentially are trying to measure here is, we write this out as a prediction problem, but it's actually a counterfactual prediction problem. So what we are trying to measure is the expected number of clicks that an algorithm, if clicks is your outcome of interest, that an algorithm would generate at some given point in time. And we write this down as a probability that the algorithm would like give this hotel or this item an impression, conditional on a bunch of like hotel and seasonality features, and then again multiply that by the probability that it would get a click conditional on an impression. And this is the key part here, this D, which is the discrepancy features, the ranking discrepancy features. So what we are saying is that in the data, we are going to see different levels of discrepancy between ranking in the algorithm of interest and the overall cohort, right? But we are going to want to measure the true Tate, we are going to want to push this to when it's almost close to 0. That's kind of what we are trying, which is like, remember this hotel B in the middle, when the discrepancy then is going to be 0. So we're going to want to kind of be able to predict what the Tate is when these discrepancy measures are 0. So we can estimate this in some ways as any kind of a predictive model. If there was enough variation in your data that you saw most hotels, most items in some cohorts where they were close to 0 discrepancy, then or hotels like that hotel which were close to that 0 discrepancy. So you can take advantage of both panel and cross-sectional variation. So then you might be able to get close to measure, predicting Tate. And the functions themselves, we end up modeling as neural networks. You could model them in any way that you want, but any predictive model will work here. But again, we have to remember that we are eventually doing a counterfactual prediction, so your data need to have shown that variation. And that's something you'll have to just check in the data to make sure it's there. Okay, so to what do we do? We train this model on the first 15 cohorts, and we're just going to hold out the 16th as a holdout sample. And then we are going to evaluate the counterfactual performance by setting the discrepancy features to 0, okay? And this is the estimates. This is the Tate estimates that we see. As you can see, the blue dots are the Tate predictions from the model, and the red triangles are the realized predictions. And first of all, we see that the realized and the estimated are different, which they should be, because what we are saying is that the realized is the problematic one from the A/B test, and you're trying to do this bias correction, so the bias corrected version is this blue one. And there are some reassuring trends here. So for instance, we see that when in certain cohorts, the algorithm was scaled up almost to 100%, like 90%. You see that the performance that we predict and the performance in those cohorts is much closer, which means that you are, which again gives you some confidence that you are getting close to the truth. And again, the very last cohort where the 80% of the 80% of the traffic went to this one, you see that the bias is actually lower, or the relative bias is lower than in the other cohorts. So this is a comparison of just the last 2 cohorts. Remember that cohort 16 was held out. And what we find is that for example, the extent of interference or the relative bias in cohort 16, when a higher percentage of traffic was allocated to it, is much lower than 15 when only 60% of the traffic was allocated to it. So this was just on clicks. You can just extend this model and build again a model also on a very similar lines for booking, which is what the platform actually cared about, which is where their revenue came from. And we find that actually as you go further down the metrics, you actually see more bias. In some ways, that says that it's even more important to correct for bias if there are multiple levels of, in some ways, error which are going to add up. So the naive estimate. So the main takeaway in some ways is the naive Tate estimates based on A/B tests can be pretty biased. At least that's what we are seeing in this setting. And our approach helps with bias reduction. I wouldn't say it gets rid of the bias completely, but it certainly helps with bias reduction significantly. So that was a quick summary of the paper is on my website and SSRN and various other places if you guys are interested. But a quick summary is that theoretically, we show that A/B tests of ranking algorithms are going to be biased in most marketplace settings. And we provide an approach for bias reduction, which is agnostic to the source of interference bias. And if you have, as long as you have sufficient data on existing A/B tests which test the same algorithm repeatedly. You can apply this approach. And this was tested on data from one travel platform where we saw that it seems to certainly help with bias reductions. And from managerial implications, the main is to not main implication is to not naively interpret results from an A/B test of any ranking algorithms, and to use any bias correction approach that you can find. And that's pretty much it. Thank you so much for.
Cool. We'll get to ask Hema more questions in a second. I wanted to ask one clarifying question. It's just, what's the role of the actual experimental variation here? It seems like one low discrepancy case would be where you just actually do launch the algorithm to 100%, and then maybe you're just doing time series experimentation. So what's the advantage of having actual traditional A/B tests going on here?
That's a good question. So here, the main reason you might have A/B test is if you have multiple algorithms that you're testing, then you would instead of just scaling each one by one, you might just try them at different mixes repeatedly, and continue that instead of just going with one all the way. And what you do need is enough observations where most items are in some low discrepancy. Okay, or items like that. So you can exploit both panel and cross-sectional variation. So in some ways, experimentation usually, I would say, exploits randomization within an experiment. This is also exploiting randomization across experiments. Good question.
Cool. Yeah, thanks a lot. And we'll I think that they'll control that up there. You don't need to turn that off, actually.
Okay.
Yeah.
Thank you.
Yes. Yeah. Thanks a lot. So our next plenary speaker is Susan Murphy from Harvard.
Okay, it's great to be here with all of you. Actually, I'm really fortunate I'm getting to follow Hema because the problems we work on, it's like we're at the exact opposite end of the world. So it's totally cool. Our lab works in health. It works with individuals in trials. We run reinforcement learning algorithms in trials of individuals, patients who are struggling with some chronic disorder. This means the sample sizes are not big, fortunately, right? Today I'm going to talk about one setting. We ran reinforcement learning, and I was really excited because some of the results we got from that, I thought, oh man, I'm going to put this in all my grant applications, and I'm going to get a lot of money. And so, but we have to worry about that. We want truth in advertising. That's what this talk is about. It's our first steps in that direction. I'm really fortunate to work with a large number of collaborators. I think Kelly is somewhere in this room. I haven't seen her, but it's great to have a large team, behavioral scientists, computer scientists, even an electrical engineer in here. Okay, so Heart Steps, this is a study of 4 people who they were just diagnosed with stage 1 hypertension. This is a unique time. If you're fortunate, you're able to change your behaviors, the chance is you can increase the chance that you'll never have to go on drugs. So it's a great time to try and change your behavior. Pedja Klashnia is the PI here. It involved an app on the phone and a tracker which tracked both sleep and step count. And like I said, we ran an RL algorithm. Notice the sample size here. This is not all that unusual in these settings, 91. In these types of studies, there's usually multiple components. For example, the current version of Heart Steps has 6 components. And today I'm only speaking about one of them. Okay, so these are multi-component interventions. And this component is about trying to help people be more active as they go about their life. And they can receive at any of these 5 times a day. It's their user-specific times associated with that person's, the way they manage their life. And the notification that can appear on their phone is, it's tailored to the sensor data that's on them at that time. So like the current weather, whether or not they're at work, and so on. And you can see an example here on the left-hand side. I got this early in the morning. It was a pretty cold day. So you can see how the framing is trying to help me be a little bit more active in the near time. So we focused on, and in the reinforcement learning algorithm, it focuses on whether or not to send one of these notifications or not. And there were different types of notifications. But the reason why we focused on whether or not to send is because all of the iatrogenic problematic effects occur from sending too many messages at the wrong time. So we really want to learn when is it best to even send, reach out versus not. The outcome here is near time. It's their near time 30-minute step count. And this is common in this setting because the content of that intervention is tailored to where the person is at that moment in their life. When you think about how the algorithm progresses, this algorithm was run separately on each of the 91 individuals. The data that you see, it's classical in these reinforcement learning settings. You see state, action, reward, SAT. And it's important to remember that during the study, the action it's the algorithm selected action. The reward, which is an outcome, is the algorithm's reward. It's not the individual or the patient's reward. It's the algorithm's reward. And the algorithm uses this reward to learn how to select the actions. At the very bottom in blue is a little bit of notation. The expected, in this case, log of the 30-minute step count given current state and action is denoted by lowercase r. The state here, I already mentioned, it includes your location, includes how variable your activity has been over the last week, includes the current weather, includes whether or not you're at home or work, and so on and so forth. Okay, so this algorithm was run on V2 and V3. This was in Seattle, not at UW, but near UW. It's the goal of the algorithm is to maximize the sum of the rewards, this sum of the immediate activity by the individual. So if the algorithm is working well, the person should be more active in the near time because those suggestions are actionable. Now, in all of these cases, when you're talking about reinforcement learning, the use of reinforcement learning in clinical trials, you're actually talking about a whole series of trials. These are not one trial and then you go and you implement it and that's the end of the story. That's not the way that you play this game. It's actually a hierarchical sequential decision making. The highest hierarchy is you have an implementation, you look at the data, you revise the algorithm, you may even revise the action space, you have another implementation, you look at the data. So there's a human in the loop at the higher level, and the lower level is automated. So that's the reason why I had this second little, oops, I don't know how to do this. How do I get a dot? Oh. Here, this is why I had this second thing here, facilitate between study learning. That's taking into account the fact that there's a higher level sequential decision-making problem going on, as is always the case. Okay, so what HeartSteps did is it implemented a generalization of the classical Thompson sampling algorithm. It's the simplest of all the reinforcement learning algorithms. And the way I think about this is I always separate these algorithms into two parts. The first part is a learning algorithm. And if you're from data science or statistics, it's fitting some sort of model to the data. It may be a very complicated model, depends on the amount of data you have. We don't have a lot of data. This is occurring in real time. So we use relatively simple models, trading bias and variance. So in our case, the learning algorithm is a Bayesian linear regression model for the expected reward given state and action. And then the second element of all these algorithms, the online setting, is how the algorithm selects the actions. Here the action is binary, send a suggestion versus not. And here in Thompson sampling, this is posterior sampling. You can see at the very bottom of the slide, let me try and use my pointer again, that in classical Thompson sampling, there's no the threshold is 0. And so what the algorithm does is it calculates the posterior probability that in state S, the advantage of sending a suggestion versus not sending a suggestion is greater than 0. It calculates that posterior probability. If that posterior probability is high, the algorithm is forecasting that it's worthwhile to send a suggestion. If the posterior probability is low, the forecast is low. And it uses that posterior probability to conduct the randomization. So with greater probability, one gets a suggestion if the forecast is indicating it's worthwhile. Now, in this generalization, there's a threshold, as I pointed out. And if you're familiar with full RL, in which it's you use a Markov decision process, this threshold is built off of prior data, and it's related to the value of the next state when you send an action versus when you don't. So this threshold will be high if the value of next state indicates that you're going to induce burden and a decay in treatment effect in future. And thus the immediate threshold is higher. It has to achieve a higher threshold to get a greater probability. So I'm going to ignore this from now on. We're just talking about what was implemented here. I can talk with people about the actual algorithm if they want afterwards. Just to keep us all on the same page, just talking about the advantage of sending a suggestion in state S versus not. That's that difference. It's just a linear combination. Theta is only 5 dimensions. The first is the intercept, and you see the different features, very simple features. Traditionally, the features are all summaries of the individual's past history, and also in some settings, very frequently, actually, they're predictions of engagement, predictions of receptivity, and so on. Okay, the last feature is the variation in physical activity. It's whether or not one appears to be increasing their variation in physical activity or decreasing their variation in physical activity. Okay, so we ran that algorithm, just like I said, and we're looking at the results of the algorithm from one person to another in these 91 individuals. And Thompson sampling, it's a great algorithm. It's known, it achieves a very high quality regret bound. We know that it works from a theoretical perspective. If you're a theoretician, it's over, you're done. It's great. It's a great algorithm. Why am I even bothering with this? But a lot of decisions, remember there's that higher order, higher level sequential decision-making process with that humans in the loop. And we really need to know, do you want to spend? It's expensive. It takes a lot of time to put these algorithms into the field. They have to be autonomous. They have to be stable. This isn't a real clinical trial. A lot of decisions have to get made at that higher level. It could be that the intervention content is useless, just causes burden. We need to understand that. So there's a whole bunch of reasons why you might want to look at a postmortem. That's the case here. So, and what we're going to focus on today is if you see a graph or a figure that looks extremely striking and you think, oh yeah, this is the one I'm going to put in my grant application. Is that striking graph just due to stochasticity? So let's just think, so we're all on the same page, let's think of a classical setting. Suppose I'm taking numbers from 0 to 9. I have a random number generator, and I'm just going to generate a digit one after another, a long, long sequence. You may look at that sequence and see this long run of 5s and tell me, oh, Susan, no, this is not a uniform random number generator. You got a problem here. But we know just from stochasticity, you can get runs of 5s. Doesn't mean anything. It doesn't mean a thing. And that's what we're worried about here. So I'm going to show you some pictures. And the question is, could these pictures that have occurred, are they just akin to a long run of 5s, which just could occur by chance? So these are 2 individuals in this study. The x-axis is the day they're in the study. Both of these individuals were looking over a 3-month period. This was in Seattle, started in 2019. The y-axis is the algorithm's forecast of the effect of sending a suggestion versus not. It's a standardized forecast. That's why the scale on the y-axis is between 2 and -2. It's a standardized forecast. And so the higher the forecast is, the algorithm is stating on that day, at that time, the algorithm forecasts that it's worthwhile to send a suggestion, activity suggestion. So the higher the forecast is, the greater the algorithm is putting behind sending a suggestion. Now, the posterior sampler, that probability is a 1-to-1 function of this forecast, okay? So that higher that dot is, the greater the probability the person will get the suggestion. So on the right-hand side, well, on user 2, which is my left-hand side, this was totally cool. It looks like at the beginning of the study, everything starts at 0, no effect at all. And then lo and behold, it appears like the algorithm learns that for this user, it's worthwhile to pretty much send the suggestion. It's great. I think this is really wonderful. We've learned a lot. And then the other one, let's go to the user on the right-hand side. And this was cool too. Here, I color-coded the dots. Remember, these are forecasts by the algorithm, and the algorithm acts on these forecasts to determine whether or not to send an activity suggestion. So in this case, the blue dots indicate that the person recently has been decreasing the variation in their activity, and the red dots means the person has been increasing the variation in their activity. So these are summaries of their past history. So what we see here is just glorious. It's just like, I really want to put this in my, so this is totally glorious. What it's saying is, look, if the person has been recently decreasing the variation in their activity, the algorithm is forecasting that you should send a suggestion. Not only that, remember, these are algorithms with a feedback loop. These algorithms, they make a forecast and then they act according to that forecast. And then the algorithm gets a reward and then it redoes its forecast for the next time. So the fact that this is spreading out, this picture, remember, I'm naively interpreting this for you, indicates to me that the algorithm is really learning that when this person is decreasing in their variation, that's the time to send a suggestion. We're getting stronger and stronger forecasts as time goes on. This is totally cool. Are these sequences of 5s? That's the question. Okay, I'm going to talk about user 1, and it's a very positive answer. User 2, I just want to tell you, I don't have time to talk about user 2. It went all, there is just no evidence there, no evidence. Okay, so I just want you to, some truth in advertising here. I'm going to show you the positive result here, not the negative result. Okay, so what, that y-axis, that forecast, it's, the numerator is this, it's this standardized delta hat, this forecast. You see the numerator is the predicted advantage minus the threshold divided by the standard deviation of that prediction. And again, the probability that someone gets a suggestion is a monotone function of this standardized forecast. So the first challenge we have is, how do you characterize a graph, like these two graphs, that appear that I want to use to sell this algorithm? That's the first thing, and then we'll go on to how do we then assess whether or not that's just by chance. So what we're going to do is we take that standardized forecast, the predicted treatment effect. Here, because we're focusing on user 1, we're going to look at states where activity is high, increase in activity is high, versus states that's z=1, and versus states where z=0. So we have a predicted treatment effect for two different kinds of states. And we look at that person, this is I'm talking about the first bullet point. We look at that person over time and look at what's the fraction of times over time that the forecast that if they're having high activity is a forecasted treatment effect is greater than the forecasted treatment effect if their variation in activity is decreasing. Now, the graph I have at the top of the slide, this is going to be a setting where the positive fraction is very low because the blue dots correspond to z equals 0. So a high or a low positive fraction is a way to operationalize this graph. And we're going to look at users. We're going to count the number of users that have a high fraction greater than 90%. So 90% of the time, it looks like it's better to send when z is 1 versus not, or only 10% of the time, it looks like it's better to send when z is equal to 1. That graph is at one of those 10%. Okay, we're going to count the number of users. And on the next slide, you see a large number of users have graphs like this, around 39 users. That's kind of the length of the run of 5s. And so you're thinking, well, maybe there will be some evidence. The question is this spurious? Is this just a run of 5s? Why am I worried about where's this stochasticity coming from? I just want to make sure, I want to make sure we're all on the same page. Posterior sampling is a stochastic algorithm, right? So we're looking at the stochasticity. By chance, we'll just see this picture, and it's due to the stochasticity and the action selection. Okay, so how do we determine whether or not 39 is a large number or a small number? If 39 is a large number, then we feel pretty good. This algorithm is actually doing something. We can proceed further optimize the algorithm. So what we do here, there's all kinds of primary analyses for these clinical trials. These are heavily regulated trials. I'm not talking about primary analyses here, a part of the regulatory part. I'm talking about exploratory data analyses after the fact. So what we're doing is we decide to do model-based resampling. And the reason why we have to do that is we have to construct potential outcome trees. Very similar in a way to what Hema was doing, except I only have 91 users, so I have simple models. There's nothing deep here. No deep learning. So here's remember theta's 5-dimensional, the baseline covariance G of S, that's a much larger vector of features. So what we do is we obtain the posterior mean for theta at the end of the study for each one of the users. We calculate their user-specific residuals at each of the time points during the trial. We retain the state residuals and the posterior means that were obtained at the end of the study. And from this, so I'm on the second bullet point right now, from this we create potential outcome trees. And by altering the weight on the treatment effect, we can produce different ground truths. Now I'm interested in the ground truth that variation has no impact whatsoever, yet I'm seeing these beautiful graphs. Okay, so what we're going to do on the next slide is we're going to set the theta entry. Theta is only 5-dimensional. It's the last entry. We're going to set that last entry to 0 and then rerun the RL algorithm over and over again. And what do we get? We did it 500 times under this ground truth that there's really no effect of variation. And here you see the histogram of the number of users in each one of the 500 trials, right? So the histograms, there's 500 trials here. And lo and behold, there's just, if that theta weight on variation is 0, you just don't get anywhere near 39 users having a graph of this type. Glorious. Now, again, I just want to emphasize to you, we did this for the other one too, and it did not look good at all. So, it's not, I just limited time here. Here's my last slide. I have my QR code. You can find the paper if you look there. So my question to you, this area, as best I can tell, is completely open. How do we do a better job investigating, doing a post-mortem analyses? If your model's incorrect, you noticed I use model-based resampling, very simple model. How do I investigate it if I'm concerned about the quality of my model? How do you theoretically justify this? That's something we're involved in. It's of interest to us as well. There's just a lot of work to be done in this area. Thank you.
Cool. Well, while Hema's joining us, I just had a first question for you, Susan. So the case that you were just considering there is sort of this null of no learning whatsoever, and
In that particular state.
yeah,
Yeah.
and or about those this variation state. How do you think? I mean, this is often an issue with these kind of Monte Carlo tests. How do you think about how you might test other nulls of sort of some learning but not enough or something like that?
So here, that's the open thing, is after the fact, how do you test whether or not there was learning? And here it was too many users showed this graph to be due to chance. Now we're also working on it where you take into account some of the stochasticity in the sampling of the users from a population, right? This conditioned on the users. There are primary analyses here. There's something known as a causal excursion effect. So in a setting where you're talking about sequential decision making, you always want to, at each time, you got to that point in time according to some schedule of action selection. So you ask, what's the effect of deviating from that schedule? Just small excursions into the future. It can go over multiple times over the next week, just over one time. And you compare those excursions. And that's where all the primary analyses, and those are guarantees to the funding. So the sample size is determined by this, to obtain a certain amount of power, to detect particular pre-specified. So this study is on clinicaltrials.gov. You have to pre-specify the primary analyses. It's a highly regulated world. But in terms of the exploratory data analyses to inform that higher level decision making for optimizing the algorithm, that's an open game.
Yeah, very interesting. I mean, it seems like just a lot of times people are either in this mode of doing statistical inference or just kind of exploratory data analysis in a way that tries to be totally model free. But I mean, it's interesting you kind of bring this model into that process.
It's because of the higher level sequential decision, the human in the loop. I think Hema is one of those experts in our loop, kind of.
I don't think so, but again,
not in the health field, but in the.
Cool. Do we have any questions? I think we've got a couple of mics roaming around. So if you have a question, raise your hand. I have another one about the interference setting, and just thinking about. You briefly mentioned this idea that maybe we don't need to look for the exact same item, the exact same hotel being in the exact same position, but we might be able to use sort of looser ways of comparing similar situations. And maybe you can say a little bit more about that.
Question. Yeah. So in principle, there is like the ideal variation is just panel variation, right? Like every item we are finding it in its exact position, but maybe I don't have an item in that exact position showing up, but maybe there is another item like this item, which is in its equilibrium position. So we kind of think of this, like in the paper we talk about it in more detail, but intuitively we can think of this as exploiting cross-sectional variation. So items which are similar to this item, how close they are to then even if I have an item A, which is never in its it's never in like low ranking discrepancy across items, but another item which is very similar, and then that's where you have notions of similarity that you need to kind of have, which is some metrics. In this case, we have some latent features of the hotel and so on. So if you have notions of similarity between items, you could exploit that cross-sectional variation.
And that may still account for some forms of interference, but other things, I mean, I guess if they are two distinct items, they don't necessarily have the same supply constraints or something.
Exactly. So to the extent they are similar, it will account for it. But to the extent that they're, if they are not, if they are different on some dimensions, then it's not going to work. And that's why we think of it as a bias correction rather than completely getting rid of the bias.
Can you get some idea of the demand, the supply constraints? When you think of this similarity, do you have access to that kind of information?
So you usually might have access to how many other people searched for something, or the star rating, or how big the hotel is. Like
Yeah.
if it's a small
Yeah, like a
inn
boutique.
versus
Yeah.
like big.
Yeah.
Again, but that depends on what data you have and to what extent can you make that connection.
Well, and it may be even if you know something about the number of rooms available, the hotel's going to adjust the prices
Exactly.
as those are.
And the price responses could be different across hotels. So.
Cool. I think we've got a question from David.
Hi, Hema. I was wondering. So, great paper. You mentioned the assumption that there's no sort of interference across items, which when I was reading the paper, I was like, wow, that's a very strong assumption. But then the empirics seem to suggest that the method works pretty well despite the assumption. And I guess I'm wondering if you have any thoughts or intuition as to, is that actually just generally not something that we should be worried about? Is that something idiosyncratic to the setting that you're studying? Like, I'm just wondering if you thought about that at all. And
we did. And we did think about it a lot before, and we did think about it a lot during the review process as well, as you can imagine. So the assumption, the core assumption, in addition to the fact that you need the same algorithm running multiple times, is that there is no spillover in some ways between items across, right? So so what we are really relying on here is the idea that we can take out these micro slices and treat them as like equilibria, right? Which we can then like bunch up together. So in this setting, we didn't see a big effect, and we tested it. So the nice thing about this assumption is that you can test to what extent this is true or not true. For example, you can look at whether the demand, if you have variation in where an item is and what is shown around the item, you can test in the data whether the demand for the item, to what extent is it driven by items around it. And you can just empirically test for it, and it may or may not hold. If you feel like it seems to be strongly affected by items, neighboring items, then this is probably going to be giving you much more, you're not going to go very far with it, but if it not. So, it's a strong assumption, but the good thing is you can test for it very easily, and that's what we do.
Thanks.
Cool.
Hi, another question for Hema. So, thought the results you presented were super interesting. The question that popped into my mind is like how generalizable you think. So you presented it on sort of the one algorithm, right? Would we have to do this for every single algorithm we wanted to do this procedure, or could we take like, oh, we did this for one, and this is like maybe generalized to other algorithms in like the same class? And an extension question that's second is, how do you have a sense of what's like the optimal number or recommended number of experiments we would need to sort of repeat with the same algorithm?
Yeah, both good questions, very practical questions. So if you ran a different algorithm, and if that algorithm was different, you would need to try again run the bias correction for that algorithm, unless and until like there is some clear way in which you think they map to each other. But otherwise, you would have to run it and that's partly what you're trying to learn, right? Which algorithm is better. So you would have to do the bias correction for both and then compare both. In terms of what is the ideal variation that you need, that's again a very good question. There is no good theoretical answer that I can give you that you need so much variation or you need so many experiments. But again, the good news is that you can test in the data. For example, you can look at, for all the items that you have for the algorithm of interest, do you have at least one cohort where it's close to the ranking discrepancy is close to zero, or items like that which have ranking? So you can test for so essentially there is a fundamental identification argument here, right? For that you have this panel and cross-sectional variation. You can just take the data you have and see whether you have achieved it. And that's, but there is, what would be nice is if we could I think what would be a really cool thing go forward with this is to, what is the ideal variation that you would come up with? Like, how do you create this ideal variation? And we haven't done that, and that's something I think is very interesting.
Yeah, so actually kind of thinking about the connections between both of these talks, one of the sources of interference sometimes can be actually kind of data or learning-based interference, where an algorithm, if you only give it, a small amount of traffic, maybe not really getting to learn that much about the action space, or maybe cheating by getting all the free randomization that's coming from some other algorithm, and it's just doing an exploit, and so it can look really good. And so I wonder whether you think that's a core part of what you're seeing there, and then Susan, whether that's something that you've thought about as well in some of those kinds of settings, especially if you were going to be borrowing information across people or something like that.
So we
I'll
do.
let you take this.
No, exactly right. So we do have a study right now in the field where the algorithm is borrowing information across people in real time, and it's in right now. But I guess I don't understand the question. I mean, there's a lot of issues there. It's a bias variance trade-off, right? These are very heterogeneous people. It must be the same. It's the same with the customers and the companies. Yeah.
I guess I'm thinking of a case where you could have your 100 people either allocated all to one algorithm, in which case there's a lot of room for borrowing of information, or if half of them were allocated to one algorithm, half to another, then either there's less data for the algorithm to be learning from or less to borrow, or it's kind of cheating by borrowing information from the exploration that some other algorithm is producing.
Yeah, so for us, these are optimization, these series of implementations, these are optimization studies. So there's a whole bunch of simulation work with actual data that goes on to compare different RL variants. But then once you get a variant, it goes into implementation. The cost is just way too high for like 91 patients. And then you get to change it, but you only change. So it's a sequence of algorithms as opposed to multiple algorithms running simultaneously. That's the big difference, I think, is we're in a sequence of algorithms. And so we do borrow, it's transfer all over the place, right? So you use information from the prior implementation to form the warm start for the next implementation. So there is transfer there. But there's not this pooling in real time because it's only one algorithm. I mean, each one, it's a different variant they're getting optimized as you go through. Yeah.
But they run over all the 91 people separately. So if you saw that you and I were like similar, we wouldn't say, let's like do
and
it
our studies, and the study we're running now, we look at similarity between people.
And then like run the same on both of them.
Or they share data to the extent that they're similar, right?
Okay.
Not potentially complete sharing. And it's also your similarity with someone else may depend on your current state. So like right now, if we all get an activity suggestion, none of us are going to do anything, right? So in this state, you could completely share our data. But in other states, we act very heterogeneously. So the amount of sharing is really a state dependent. Yeah.
Very interesting. I think maybe we can take one last question, if there's someone over here. Yep.
Hi, question for Dr. Murphy.
I can't see the person. Oh, I see you.
I'm way over here. I'm at the very edge of the... So I had a quick question. I love your work. Big fan of a lot of your papers. I had a question about this one. Maybe I didn't understand, but the question of did we personalize, is there a reason why you look more at what seemed to me kind of like outcome variables rather than maybe looking at the specific parameters and how they changed in your model from your online updates as it's running? Because the question of personalization to me might be simply, my coefficient that I multiply by the second feature is different from person A to person B.
Yeah, so the primary and secondary analyses in these clinical trials, that's exactly what they do. They look at overall effect, and they look at moderation analyses. So in certain states, do people tend on average to be more responsive versus other states? Are certain combinations of variables? And of course, that's really important for the domain science, right? The health science, because, this really stems from truth and my concerns about truth in advertising. Right now, it's just AI is, we're really getting a bad name. We've had quite a few fiascos because we overpromise. And in health, I really want AI to play a big role. And so I want, when I show people a graph that appears that things look great, I want to have some confidence that that graph is really communicating a signal. So it was it had this exploratory data analysis point of view. But I'm like totally with you. Like there is a whole host of secondary and primary analyses that go on, and these tend to be pre-specified. The secondaries are rank ordered usually. Yeah, I hope I answered your question.
Cool. So I think we're out of time at this point, but hopefully you could find either our speakers around during the break. So at this point, we're going to head into a break, and then let me make sure I'm looking at the program like all of you, that we'll be heading into the first parallel sessions at 10:35. If you're a presenter, please go ahead and do that. So let's give a hand to Hema and Susan.